the system is always in thermal and mechanical equilibrium with the surrounding is known as a quasi-static process. In an adiabatic process, the change in heat, that is delta Q, will be zero. That kind of processes are known as adiabatic processes. Keeping the temperature constant, I'm changing the volume from V1 to V2 by giving certain amount of energy to that particular system. The cyclic process is when a process returns to its initial state. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about some thermodynamic properties. So let's get back into the thermodynamic world and see what awaits for us. So we actually discussed what happens when heat interacts with the system, how heat is given to a system, what is the special relations, and what is thermal equilibrium and all. Now we'll study what certain processes are and how heat is used to do work. So first, let's start with the process that is known as quasi-static process. So what is quasi-static process? Literally, quasi-static actually means that it is a pseudo-static process, which means it doesn't really happen, but it does happen. It is that kind of a process, which means that the exact definition would be much more helpful and understandable for you if I explain it like this. Now, imagine that I have a piston arrangement and I have a piston which is easily movable without any friction or anything. Now, what happens if I drop one molecule on top of this particular piston? Not one rock, not 1 kilogram, not 1 gram, not 1 microgram, but a literal small molecule. So from the outside scope, it doesn't make much more difference, right? But at an atomic scale, it is still putting some pressure and it is still moving very slightly. That is, it is moving very slightly, like at the microscopic scale. Now, imagine that after some time in the sense after 1000 years, after 100 years, like that, I'm just dropping one molecule like that. So it just so happens that every 100 years or 1000 years, I am making this piston move slightly, which means that the piston is moving, but it is not visible for us. It is like that the system is in equilibrium and the piston isn't moving at all. But in actuality, the piston is moving, but it is at a very slow rate. So that kind of processes where the system is always in thermal and mechanical equilibrium with the surrounding is known as a quasi-static process. It is an infinitely slow process so that the equilibrium state is not disturbed. It is not practically possible, but it is an ideal state or an ideal mechanism which we can imagine in the world of physics. So we can define a quasi-static process as an infinitely slow process in which the system remains in thermal and mechanical equilibrium with its surroundings at every stage. So at every step of the way, the equilibrium is maintained. So every step of the way, the equilibrium is maintained. So it is like we are performing the experiment in infinite amount of time. That is, we are making it extremely slow, infinitely slow. So it is not practically possible, but rather an ideal concept. Now, we are going to discuss how heat can be used in order to do a certain amount of work. So before doing that, we have to know what is certain types of processes. For example, isothermal process, isobaric process, isochoric process, and adiabatic process. So again, you might have seen what is adiabatic. That is, in the earlier session we discussed that adiabatic means that there is no heat exchange, which means in an adiabatic process, the change in heat, that is delta Q, will be zero. That kind of processes are known as adiabatic processes. And now, what is isochoric process? In isochoric processes, the volume will be constant. That kind of processes are known as isochoric process. For example, iso means it is same. Choric means it is a Latin word for volume. So we can say that isochoric means that it means volume will be constant. And just like that, isobaric means same pressure. That is, barometer is an instrument used to detect pressure. So you have to know that baric or simply isobaric means that it is at constant pressure. That is, pressure becomes constant. Then automatically isothermal process. Isothermal means iso meaning same, thermal meaning temperature. So here temperature will be constant. So these type of processes will be very common in the field of thermodynamics. So we have adiabatic process, isochoric process, isobaric process, and isothermal process. Now in all of these processes, we are going to see how heat is used to do a certain amount of work. So first we'll start with the isothermal process. So first we'll write down the equation for work done, that is W is equal to P delta V. But this equation again is only possible if it is at constant pressure. If the pressure is varying or it is a variable, then we have to use the equation, that is the variable equation, volume changing to V1 to V2, P dV. So again, since pressure is not a constant here, I have not specified that pressure is a constant here, I have to use this particular variable equation here. So I can say that since pressure is not a constant, I have to write work is equal to V1 to V2 integral P dot dV, or simply P dV. Now, one more thing you have to remember is that the ideal gas equation, which dictates PV is equal to nRT. So these two equations you have to remember before you start this particular derivation. That is the ideal gas equation and the variable work done equation in terms of pressure. So both are done. Now we are going to start our derivation. That is, we are going to consider that what happens when an ideal gas expands from V1 to V2 volume. So here I am allowing a gas to expand from V1 to V2. That is, here I have a container. In this container, I have a certain amount of gas filled in this particular container. I am giving heat, that is Q, heat to this particular system. Given that this particular region, in this particular condition, in this particular system, the temperature is not changing, but I have to change its volume. So, keeping the temperature constant, I am changing the volume from V1 to V2 by giving certain amount of energy to that particular system. Then the gas expands, the volume increases from V1 to V2. So what is the work done in that particular process? That is what we are going to find out. Again, if you're having a hard time imagining how that happens, just imagine it like this. If you perform anything very slowly, any particular task very slowly, the temperature won't change much, but the pressure, volume and energy will be changing in that particular form factor. For example, imagine you're pumping air into a cycle tire. So if you're doing it very slowly, then what happens? The piston, it is very similar to a piston arrangement. The piston will be going down, the volume will be changing, the energy is given to the system and the system is going up and down, which means we are doing a work. So the volume is also changing, the pressure is also changing. But there is no change in temperature because we are doing it very slowly. The same pump, if you pump it really fast, what happens is that the temperature will change. You can actually feel a change in temperature. That is a certain scale of temperature on the pump because you're pumping it very fast. Their energy is conserved, but temperature changes. It is an adiabatic process. Here, if we do it very slowly with the cycle pump, then it is an isothermal process. Energy is changing, but temperature is not changing. So again, we are going to find out what is the work done in that particular process. So we know that from the ideal gas equation, PV is equal to nRT. Now, if you look at the right hand side, we can see that N is the number of moles for a given volume of gas, that will be constant. R is the universal gas constant, which is having a value of 8.314 joules, Kelvin inverse, mole inverse. So that is also a constant. And finally, temperature. In this particular process, that is an isothermal process, temperature is also a constant, which means these three quantities together, we can call it as one single constant, and I'm calling it as K. So I can say that PV is equal to K, or simply P is equal to K by V. I'll mark it as equation number 1. Now, I'll substitute this particular equation in this particular work equation. That is, work done is equal to integral V1 to V2 P dV. That since the differential sign is in dV, I'm going to convert this P into terms of volume. That is, pressure is converted in terms of volume. Then I can rewrite this as integral V1 to V2. Instead of P dV, I can write it as K by V dV. Now again, K is a constant. We know for integration, K cannot be integrated since it's a constant. It'll go right outside. Now I can write it as K into integral V1 to V2 1 by V dV. So again, you have to know this result. You will study it in your second PUC in mathematics. That is, integral 1 by x is actually equal to ln x, or simply natural logarithm of x plus a constant, but we are not considering a constant, we are taking it as 0, but here, yeah, ln into x. And one more result you have to remember is that ln of x2 minus ln of x1 will be equal to ln of x2 by x1. This also you have to remember. Why? Because when we solve it, we'll get to that particular stage, so you can apply this also. Again, don't worry about these particular how we got this and how are you going to substitute this, because all of these you will study in detail in your second PUC mathematics, but we can't go further without these results. We need mathematics to apply in physics. That is why I'm just showing you how it is done. So again, we have 1 by V here. So what is 1 by V? Again, integral 1 by V is actually equal to natural logarithm of that particular quantity. So instead of integral 1 by V dV, I can write it as, K is here, I can write it as natural logarithm of V from the limits V1 to V2. So again, this is not the final result. We have to apply the upper value and the lower value. So when we apply the upper value and lower value, we'll get the result as W is equal to the constant into ln V2 upper value minus ln V1, that is upper value minus lower value, or that simply will be written as K into ln of V2 by V1. So this will be the final result. And if you want to write it much more elegantly, you can just write it as W is equal to K, which is nRT. So K is equal to nRT. So W is equal to nRT into ln of V2 divided by V1. So this will be the final form of an isothermal process. So in an isothermal process, the equation for work done can be obtained in this particular manner. One more thing, if you don't like it in natural logarithm and if you want to convert it into textbook standards, you can use one small trick That is, instead of natural logarithm, if you want to use log to the base 10, that is the logarithms which we use in calculators and all that, we can convert it into log by multiplying this entire term with 2.303. So if you want to write it as log V2 by V1, the only thing you have to do is that multiply a 2.303 with this particular equation. So if you multiply 2.303 to this particular equation, it will be converted into log. So nRT into 2.303 log V2 by V1 will be equal to W. That is the work done in an isothermal process. Again, if you're confused with what is practically an isothermal process, where can you find it in nature other than the cycle pump, you can also observe it in your kitchen in everyday life. That is, when you boil water, it reaches 100 degrees, right? It reaches 100 degrees, it starts boiling, it starts converting it into vapor, but the water surface will still remain at 100 degrees Celsius. Water boils at 100 degrees Celsius, it is not crossing 100 degrees Celsius, pure water. So it will stay at that particular temperature. It won't increase. Even though it is boiling, even though you're giving energy to that particular system, the system is still staying in 100 degrees Celsius because the excess energy is used to convert water into water vapor. It is doing your work. So it is an isothermal process. So you can find much more examples in daily life. Now the next process is adiabatic process. Adiabatic means the heat exchange is actually zero. That is, delta Q is equal to 0. Now again, you can use the example of the cycle pump. If you're doing it really fast, that is, if you're pumping up and down really fast, then obviously there is not enough time to transfer energy to the surroundings, which means that there is a temperature change evidently, but there is no energy exchange between two systems. Here we have to use two equations. That is, we do know that PV is equal to nRT, that is the ideal gas equation. We also have to know that PV raised to gamma is equal to a constant. So what is this PV raised to gamma? Again, gamma, in the previous session I told you, after Mayer's relation, gamma is another relation which states that Cp by Cv, that is the ratio of heat capacity at constant pressure to heat capacity at constant volume, that ratio will be equal to gamma. That is expressed here again using a different equation, and you don't have to worry about where it came from, how it is obtained and all that. But it is important that you know this relation, that is PV raised to gamma is also equal to a constant, where P is pressure, V is volume. So if PV raised to gamma is a constant, then we can write P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Now, this you already know from equations of continuity, Bernoulli's principle, that if any quantity is equal to constant, then I can write it in this particular form also. So let's see how we can obtain work done from this particular equations. Again, the consideration is that a gas is allowed to expand adiabatically from volume V1 to V2. That is, there is no energy exchange between two systems, but we are allowing the gas to expand. That is, I'm giving temperature to a system, but I'm not allowing energy exchange between the systems so that the gas expands. So now we can say that work done is equal to, again, the pressure is changing, so we are using the integral sign, and we can see that volume is changing from V1 to V2, and the equation is PdV. So work done equation is given here, that is integral PdV from V1 to V2 will give you the work done. Now, instead of using PV is equal to nRT, again we are going to use PV raised to gamma is equal to a constant. So that let that constant be K, or simply P is equal to K divided by V raised to gamma. So we are going to substitute this particular result, and we can see that, okay, it will be equal to integral V1 to V2. Instead of PdV, we are going to write K by V raised to gamma dV. Again, we know that K is a constant. It is going to come right outside, which means that it is going to be K into integral V1 to V2 1 by V raised to gamma. Then again, don't do the exact same thing we did for the isothermal process, because here the equation is going to change. because, again dv is here, because we are not going to apply the same method here. That is, if we have v raised to gamma in the denominator part, that is, we have 1 by, let's say, 10 square, 1 by 10 square. Then when this 10 square comes to the numerator, I can actually write it as 10 raised to minus 2. That is, if I have any quantity, raised to the power like this, if I bring it to the numerator, I can write it as a negative sign. It is called an inversion process. So again, you will see it in your second PUC again. If you already know it, very good. So if any quantity from the denominator goes to the numerator, it is inverted, and we can write it as such. If you put a minus sign to the power, that will be enough. So just like that, this v raised to gamma, when it comes to the numerator, I can actually convert it and write it as k into integral v1 to v2 v raised to minus gamma dv. Right? I can write it as v raised to minus gamma. Since the power term is in the numerator, I have to put a minus sign. Now I am going to integrate this particular quantity. And again, we also know that integral x raised to n is equal to x raised to n plus 1 divided by n plus 1. Here, instead of x raised to n, we have v raised to minus gamma. So using this particular relation, we can see that integral v raised to minus gamma will be equal to k into v raised to minus gamma plus 1 divided by minus gamma plus 1. So this will be the equation for work done after we solve the integration part. So instead of writing minus gamma plus 1 or minus gamma plus 1 here, I can just reverse it, right? Instead of writing minus gamma plus 1, I can just simply say 1 minus gamma. So I can say it as, again, this will be from the limits v1 to v2. So again, I can say that instead of writing minus gamma plus 1, I can simply write 1 minus gamma. So I'm going to write it is k into v raised to 1 minus gamma divided by 1 minus gamma whole into, that is, from the limits v1 to v2. Now again, this 1 minus gamma is again a constant because there is no v term here. Only v, we can substitute these two values. So we're going to remove this 1 minus gamma from the denominator, take it right outside. So we can write it as w is equal to k divided by 1 minus gamma into applying the limit, that is upper limit, v2 raised to gamma minus 1 minus v1 raised to gamma minus 1. So we have our final results here of the integration part. So 1 minus gamma is outside. The remaining quantities we have to apply the limits, which means that it will become v raised to 1 minus gamma, and this will be v2 because we are applying the upper limit. So upper limit minus lower limit. Lower limit is v1 raised to 1 minus gamma. So v2 raised to 1 minus gamma minus v1 raised to 1 minus gamma. So this is the end of the integration process, but the final result is still not over yet. So again, what we are going to do now is that we are going to multiply this k inside this particular bracket. So then we can say that this will be equal to 1 by 1 minus gamma into k into v2 raised to 1 minus gamma minus k into v1 raised to 1 minus gamma. Now, what is k? We already know that k is equal to the constant which is equal to PV raised to gamma. So PV raised to gamma is equal to k. So which means that instead of this k, I can actually substitute this PV raised to gamma. So W is equal to 1 by 1 minus gamma into k will become PV2 here raised to gamma into V2 raised to 1 minus gamma minus, so this can be written as PV1 raised to gamma into V1 raised to 1 minus gamma. So here again, what is A raised to M into A raised to N? That is A raised to M plus N. Similarly, we can do here also. So the gamma and gamma will cancel each other out. That is, there is a minus gamma here, there is a plus gamma here. There is a minus gamma here, there is a plus gamma here. So A raised to M, that is A raised to M into A raised to N is equal to A raised to M plus N. So in this case, the minus gamma and the plus gamma will cancel each other out, and the only quantity that will be remaining, is 1 by 1 minus gamma into PV2 minus PV1. So again, bear with me, it's a long derivation, but bear with me. So W will be equal to 1 by 1 minus gamma into PV2 minus PV1. Now again, we know that PV, that is PV is actually equal to nRT, right? Temperature 1 and temperature 2. So if it is changing from volume 1 to volume 2, we are giving it temperature. Here only energy is not changing, but temperature can change, which means the temperature here will change. So instead of PV, I'm going to write it as nRT. So W is equal to 1 by 1 minus gamma into, instead of PV, I'm going to write nR. N and R for a given gas is a constant, so I'm not going to change that. nRT2, because temperature is changing, T2 minus nRT1. Now again, this nR is common, I can take it outside. So I can simply write it as W is equal to nR divided by 1 minus gamma into T2 minus T1. That is the equation for work done in an adiabatic process. If you want to make it a little more pretty, you can multiply a negative sign throughout this equation, and then you can write it as nR divided by gamma minus 1 into T1 minus T2. Both are same, just multiplied with a negative sign. So this is the expression for work done in an adiabatic process, where there is no exchange of energy but only difference in temperature and volume and pressure. So you have to understand that the work done here, that is this entire work done, is used to increase its internal energy. So obviously the temperature will change. So you have to understand that no energy is wasted. There is no change in energy, but the heat given to a system is completely used to increase its internal energy. So again, you can use the example of the cycle pump for this. Now the next process is the isochoric process, where volume is a constant. So what is the work done in an isochoric process? It's very simple. W is equal to P delta V. So again, I'm saying here that, okay, I'm expanding the volume at constant pressure. So if it is expanding at constant pressure and volume is constant, then I can say that change in volume is 0. So work done in an isochoric process is 0. So it's very simple. You just write down the equation for work done, that is P delta V. Here pressure is not changing and there is no change in volume because volume is constant. So we can just directly write that work done in an isochoric process is 0. What about in an isobaric process where pressure is constant? That is, pressure is constant. Then again we can use the equation W is equal to P delta V. Here P is constant, so we can write it as W is equal to P, and delta V means that it is V2 minus V1, or simply it is PV2 minus PV1. So PV2 minus PV1 is equal to W. Or again, you can use PV is equal to nRT equation like in the adiabatic process. And you can simply write it as W is equal to nRT2 minus nRT1, or simply nR into T2 minus T1. And that will be equal to the work done in an isobaric process. Compared to the adiabatic process, all these small work done are very simple, right? So if we plot a graph between pressure versus volume for all these processes, how will the graphs look? So let's start with isobaric process only. So how will the graph look? The graph will look like this, because there is no change in pressure. Pressure will be a constant, so there is no change in pressure. And what about an isochoric process where the volume is not changing? Then we see that, okay, the volume is not changing. It will look like this. It is a straight line like this. It's slightly bendy. And what about for an isochoric process? How will it look? It will look like a straight line like this, because the volume also is not changing. So pressure constant, it means it is an isobaric process. If volume is constant, it is an isochoric process, and the graph will look like this. Now, what about for an isothermal and adiabatic process? So for an isothermal and adiabatic process, the graphs will look actually like this, where this is an isothermal process and this is the adiabatic process. So again, remember, this is isochoric and this is isobaric. So these are the different nature of the graphs for the individual processes we just proved. So again, PV, that is P into V, is nothing but work done in thermodynamics. So the area under each of these graphs will give you the work done by individual processes. So as you can see here, that in an isochoric process, work done will be 0. In an isobaric process, work done will be maximum, because it has the maximum area here. It has the maximum area here. It will be like a rectangle. So it has the maximum area, maximum work done. And then it will be isothermal process because it has the second most area. Then it will be adiabatic because it has the next most amount of area, and isochoric, it has no area, so we can say that there is no work done practically for isochoric process. Now, what is a cyclic process? You already know this, but still to refresh your memories, the cyclic process is when a process returns to its initial state after completing a one cycle. So we can see that it went through this way and it came back this way and it ended where it started. That kind of process is known as a cyclic process. And in a cyclic process, you will know that the change in internal energy will be 0 because it started where it began. That is, internal energy here will have a certain value. Then it traveled here, the internal energy is changed, obviously. But when it traveled back to the initial position, the internal energy, which is a state variable, which does not depend on the path traveled, will have no change. So internal energy will remain the same. And for a cyclic process, the temperature also will remain to be a constant. If there is no change in internal energy, then obviously the temperature will also be a constant. And if you want to define the cyclic process in words, we can just say that so in words, we can define a cyclic process as a process in which the system returns to its initial state after completing one cycle. That is known as a cyclic process. And in a cyclic process like this, that is in between P and V, in a cyclic process, delta U will be 0. That is, the change in internal energy of a system will be equal to 0 as internal energy is a state variable which only depends on the initial and final positions and not on the path traversed. So hence we can say that delta U will be equal to 0. If delta U is equal to 0, temperature will be a constant. That is all for today's class. I'll come back with more thermodynamic equations and variables. Until then, thank you.